It's important that you understand the structures of things like maltose or mannose or fructose or anything like that. It is important that you know them. It is important that you make some notes about this. But I'm really just going to talk about glucose and fructose for this type stuff. So for glucose, there's really just two forms that it exists in. There's the aldose form, the aldehyde form. And for the aldehyde form, the other form, I guess I'll just go ahead and mention it, is the cyclic form. But for the aldehyde form, it has this general arrangement of being right, left, right, right. And you will understand exactly what I mean in like 5 seconds. So let's draw that out. So it's an aldehyde, obviously. And then it's a 6-carbon sugar, so that's carbon 1, carbon 2, carbon 3. It's getting crooked, I don't know why. Carbon 4, 5, and then 6. So I know that for all of these, the 6-carbon, for the most part at least, ends with an OH, and it is not a chiral center. But for the others, they follow this pattern here. And so the right, left, right, right just means the positions of the hydroxyl groups. So this is on the right, this is on the left, the right, and then the right. And now all I have to do is fill everything in with hydrogen. And it's always a good idea to number your carbons. So this is carbon 1, this is carbon 2, 3, 4, 5, and 6. Alright, so that's our aldehyde form of glucose. And I didn't mention this, but this is, I'll change colors. This is D-glucose, right? So which determines the I guess, D versus L isomerism? Well, what we're going to talk about is that the 5th prime, the 5th carbon really, has some pretty unique things about it. So the 5th carbon, in this context, the directionality of that determines the D versus L configuration there, which we've already probably talked about that, I think, in other videos. But another thing that we could say about this, and I'll switch to a different color, is that at the 5th prime carbon, the OH group, so this bad boy, is our nucleophile to convert us to the cyclic form. And I guess I should probably draw on this. It's constantly going back and forth between the aldehyde and the cyclic form. So like diabetes testing, you're actually testing for the aldehyde form that's reacting with your hemoglobin. But anyways, for the cyclic form, there are it can exist as a furanose. I'm not saying that it can't, but let's talk realistically about how much of that is going to exist in your body. Not a lot. It's not going to be as thermodynamically favorable as that of like a pyranose form. If you don't remember, a pyranose is a 6-membered ring. So the two pyranose forms that we exist, or the anomeric forms, are alpha and beta. Also, I had someone who, if you've ever worked in the medical field, you know what D50 is. That's dextrose 50. The reason why we call it dextrose is because it's this. It's the D form, the dextrorotatory form of alpha glucose. Okay, so for alpha glucose, let's draw out the structure of what that looks like. And I'm going to use these things known as Hayworth projections to explain this. It's not really helpful in understanding the reactivity of the molecule. It's not really helpful. It's kind of an oversimplified version. But what it is really helpful for is understanding the polymers that we can form with these and the type of bonds that these things are going to form and at what position those bonds are at. We're kind of sacrificing, I guess, precision here with seeing the bigger concept. But this is biochemistry. That's basically what biology is. It's just chemistry at 30,000 feet. So I start off with alpha. To draw alpha glucose, I'm going to start off drawing my 6-membered ring, and I'm going to draw it like this. It's going to be a little cramped, I know, but I wanted to compare and contrast the two structures. Probably could have done a better job of that, but this will have to do. So I'm going to go ahead and just kind of color in the underneath parts to show that it's coming out of us, out at the plane. And then I'm going to go ahead and just draw parts that are going up and then the parts that are going down. So this is what Hayworth projections look like. Your book has better pictures. Anyways, so for alpha glucose, well, I know that it's alpha, right? So the hydrogen's going to be up here, and then the OH is going to be down here. And so this is an aldehyde, right? But I could also easily substitute this H for an R group, and it would still be an alpha form. It would just be a keto form. So that's the I guess the basic structure. Now let's go ahead and fill in the rest, right? So everything else is pretty much a constant between alpha and beta. And the pattern that I remember it is for the next one, it's down, up, down. So the OH group goes down, the OH group goes up, and then it goes down for glucose. Also, right here in the up position, I have my CH2OH. And then the rest, I'm just going to fill in the hydrogens. I'm going to draw this hydrogen super tiny because he's far away compared to the other large hydrogens that are coming out at us in the plane. And that's alpha glucose, right? So let's compare what this, well, first let's number our carbons. That's another thing that I forgot to really stress that, okay? So this right here is carbon number 1 from this bad boy. We said that carbon number 5, the OH group, is what acts as the nucleophile for the cyclization. So this oxygen came here, and this formed those up there, negative formal charge, intramolecular proton transfer. You should know how that works by now. That's an organic chemistry thing. So this is carbon number 1, this is carbon number 2, this is carbon number 3, number 4, number 5, there's the OH that acted as the nucleophile, and then this is number 6, and that's alpha glucose, right? So let's compare that with his partner beta. Just like before, I'm going to draw my 6-membered ring. I can't draw straight lines in the software. It's so tragic. Coming out at us in the plane. Not the best picture, I know, but so we have stuff that's going up and down, up and down, up and down. So with beta, we said that the OH was on the top, right? That's an OH. OH on the top. And then the H is on the bottom. And this could be an R group as well if it was a ketose. But this is an aldose, so we're not worried about that. And then the rest of it, though, is exactly the same. For glucose, it's down, up, down, and then up. And then all I have to do after this is fill in my hydrogens. There. There. I'm going to draw this guy really tiny because he's back there, and then right there. And just for reminding myself, the number of my carbons, that's carbon number 1, number 2, number 3, number 4, number 5, and number 6. Okay. So some comparisons that I would like to make about this, or that I feel like are important, is for the alpha sugars, or for the alpha glucose. And it's not really the best way to draw it, and I don't have a whole lot of room to probably draw this stuff out here. But if you were to look for alpha glucose at the position of the hydroxy group in the chair conformation, the hydroxy group exists in the axial plane. So for this, the OH is in the axial plane, and if you remember what that means that it's going to be less stable and therefore more reactive or less stable. And because of this, alpha glucose at 30,000 feet for the most simplistic things, especially in the polymerized form, okay, is generally used as a fuel source. It's used as a part of combustion reactions, right? That's what my mitochondria are doing. They're doing combustion reactions to give me ATP. So that's what alpha is doing. In the polymeric form, alpha glucose is, and I'm just going to say that in the poly form, alpha glucose is totally soluble. Okay, so beta, for beta glucose, if I could fit this in here, hopefully I can, the OH group exists in the equatorial, I'm just going to say it like that, it's in the equatorial plane of the chair configuration. So if it exists in the equatorial plane, that means that it's going to be less reactive because it's more stable. So if it's less reactive or more stable, it's really not going to be something that you would want to use as a fuel. Beta glucose, especially in the polymerized form, is used as a structural support. The exoskeleton of insects, the cell walls of plants, and the cell walls of fungi is all this beta glucose structures here. The other thing that we want to say is that in the polymerized form, it is not soluble. It's insoluble, right? I don't know if you ever take like fiber. If you look on the back of your nutrition labels, you will see fiber, soluble fiber, insoluble fiber. Fiber is not something you can digest. Bacteria have enzymes that digest them, or termites have bacteria in their gut that digest them, but we don't digest them. And so that's why beans make you gassy, I guess you could think of it as that way. But this is just a general comparison between alpha and beta, and the very single differences between the two. This simple difference can explain the difference between something that would be, I mean, this is, just to really reiterate this is a French fry, okay? Whereas beta is a splinter. That's the difference, is this one rearrangement of the hydroxyl group. That's insane to me.